over the time, to navigate the ever-shifting complexity of writing a software, developers define so-called design principles to craft code that's robust, adaptable, and easy to manage. And I think they all make sense because they're built on top of various pain points that developers had maintaining large code bases. And the most famous are KISS, keep it simple, stupid, YAGNI, you aren't gonna need it, solid principles, DRY, don't repeat yourself, as well as various design patterns such as single-tone factory, and yeah, there are many of them. And I remember that in the beginning of my career, I was so adamant about using all of those principles in pretty much every single line of code I wrote. And I would go to Stack Overflow and maybe make comments about that. But with time, I started to focus on them a little bit less and embrace simplicity a little bit more. Maybe it's also because these things become natural and you can already plan ahead what principles you need to use here versus what's not needed here, instead of blindly following Uncle Bob mantras, right? And that being said, let's dive today into one group of those principles called solid, explore its meaning and how to use it effectively within Go. And although Golang is not purely object-oriented language, we can still apply solid principles to improve our Go code. And now back to solid principles, which, by the way, were first introduced by Robert C. Martin, or Uncle Bob, obviously long before he started his Twitter rants. And solid stands for single responsibility, open-close principle, Liskov substitution principle, interface segregation, and dependency inversion. And each principle plays a vital role in fostering maintainability, scalability, and testability in your programs. And so the first principle, single responsibility, tells us that a class should have one and only one reason to change. Also that a package or struct or function should have a single well-defined area of functionality. And this keeps our code more organized and reduces complexity. We will end up with smaller files and kind of less complex functions, and things will be kind of replaceable and so forth. Go obviously doesn't have classes, it has structs, but still single responsibility principle applies here quite well. Imagine struct being a kind of small unit of functionality or data, and it also applies well to packages, because ideally the package focuses on some single area of functionality. Good examples from Go standard libraries such as encoding JSON. Actually, it's been split into encoding JSON and encoding JSON text, but also packages like net/URL and etc. Not so great examples would be a package called utils or shared in your codebase, right? Because it mixes kind of different concerns and generally hard to maintain. Cool, so let's jump to our coding editor and play with some Go structs. And for this example, we can define a simple survey type, for example. So I'll call it maybe a package survey. And our type will have, let's say, a title and also a list of questions. For simplicity, let's just use strings for now. And let's say our struct has some functions on it, right? So in Go, we can use this syntactic sugar and maybe something like getTitle that returns a string. So we can actually use have title as unexported, but doesn't matter in this example, right? And maybe similar for get questions. Or maybe let's not do get questions, let's say there is a validate function that returns an error. Let's say for simplicity it returns if the length of questions is greater than 0. So we'll consider our server valid in this case. And imagine it has another weird function here. And I already told you weird, but it's called save. And maybe returns an error, right? And maybe we'll hear save survey, right? And here it's because it should be Boolean. And so our struct and package seem to be designed well, except the part that I already mentioned is the save function, because currently we are mixing both the survey logic as well as the database logic in the same struct. And so the maintenance, the testing becomes more challenging. What we could do instead is get rid of this thing, and maybe let's define the interface, for example. And we'll be touching another principle here, but I won't mention it here. Let's say we'll define the repository as interface, right? And it will have a function called save that will take the survey. And it will return an error. So that's the interface. We can create the implementation. For example, we can create the implementation called in memory. In memory. And because it's in memory, let's say we have some sort of slice here, right? So slice of surveys. Now what we can do instead, or also we need to, on our, let's say, repository, on this in-memory repository, implement the function save, right? So it should also return an error. And we can do something like, maybe just append to what we already have. So that's just an example implementation. Obviously, it could be your Postgres implementation, your maybe file disk implementation, and so forth. And we add an S here, and then we return nil. And now, as you've seen, we don't have the save function on the survey, so this is separate. Ideally, this repository goes into a separate file package as well. But let's say we can then now define the function kind of save survey that would receive the survey and also the repository, which is the interface. So something like that. And error, and we don't know the implementation of the repository just yet, and we can do return repository.save and pass the survey there. So I wrote everything in a single line, but for the separation, let me just kind of put a line here between, right? Oh, actually, and this interface should go here as well. Cool. Now, as you can see, the survey just manages the server logic as well as its data like title and questions, and maybe validation function can happen there. And we have a data layer in separate place. It could be a separate file, obviously, but for simplicity, it's all here divided by this line. All right, so let's move to the second principle. It's called open-closed principle, and it tells that modules should be open for extensions and should be closed for modifications. In a nutshell, it means that if you already have some existing module and want to extend its functionality, it's much better to extend it kind of by adding new classes and implementations rather than going to existing functions and modify the code inside them, because it reduces the risk of introducing new bugs in the existing functions. Now let's get back to our survey struct. We kind of did something similar here, but I want to start from scratch and introduce kind of a new function. And we will do kind of the survey export, right? Maybe we'll have a function, export survey, that takes survey as the first argument and maybe the destination where to export it. And maybe it returns an error. And we can do switch on destination, because there could be multiple destinations. Let's say we can export to S3, right? So export to AWS S3 and maybe return nil. Maybe we have another option as GCS, for example, in the future. And then we are also smart, so we want to validate it. So on the default, we'll maybe throw an error, right? So return, let's use maybe errors new, or maybe let's use fmt errorf instead and do something like unsupported DST. Obviously, I miss the implementation of the export itself. Here, it could be, for example, putting the file to a S3 bucket, very similar to GCS. Maybe we can add the file and then read to your file. But you can already see that this violates clearly the open-close principle. Because imagine after some time, I'm coming back to this code and I want to add another export destination, let's say to another cloud, right? So I need to modify this function again, and that's prone to introducing new errors. And what's even worse, this function can be a part of some package or external library that's not so easy to modify, right? And you probably shouldn't do that. Instead, you should have a way to extend this functionality. And again, interfaces can be used here, right? So we can start by defining our exporter interface, right? So and then in Go, you usually call interfaces in this way, right? Kind of writer, reader, exporter. So that would be an interface. So it's very similar to what we did with database repository. And single function, again, export, and maybe server. And maybe for now I will skip an error, but it will be here. And the first implementation would be, so let's say S3. So we can have the type called, let's do S3 exporter, cool, for now will be empty, right? And then a function on this type. So let's say exporter, right? S3 export. Right now, what we need to do, just copy the implementation and introduce another implementation, which would be GCS exporter. And so inside of this export function will go the implementation, right? And now we can come back to our export survey, and the destination will be maybe the name of the interface, right? And maybe we can call it not destination, but exporter. And all of this switch will simply become exporter.export and then pass the survey. Obviously, let's just do for now like that. Actually, no, that doesn't look great. So let me properly introduce errors and errors. So we'll do error here, and then error here, and here for now return nil. So now this code listing explains the open-close principle quite well. The closed part is export survey. We write it once, we write it well, we handle errors there, and then we rarely modify it in the future. And then extension happens right here because we have the export as an interface, and to extend it we only need to add the implementation of it. For example, for a file we'll do something like type file exporter export, and then write to a file, right? And we can add as many implementations as we want. We can remove all the implementations and so forth. All right, let's jump to the next principle called Liskov substitution principle. In a nutshell, it ensures that objects can be swapped without breaking the program. And obviously, again, in Go we don't have inheritance, but interfaces can achieve that. Because in Go, any type can implement the interface by simply implementing all the functions defined in this interface definition. And to properly explain the Liskov substitution principle, I must mention the best Go interface of all times. It's io.writer. So somewhere here, I mean, there is a reader as well, and then there are others, but let's focus on the writer. So there is a really simple interface called writer with a single function write that takes the slice of bytes and writes to a stream. So let's jump back to our code and maybe introduce a new kind of place module called maybe send.go. So maybe we want to send the survey somewhere. Again, package survey. And let's say there is a simple function to send it somewhere. So send, I mean, maybe over the internet, for example, or send over some socket. So it could be send survey that takes again the survey object. And here, if we wouldn't follow the Liskov substitution principle, we would maybe add something like URL where to send it, so very specific. Instead, in Go, you would usually do the writer, and we can just do it with W, and then it's io.writer. And maybe it just returns a single error, right? So let's say we always want to send it as a JSON representation. So we can do json.marshal. We can pass as there and maybe handle the error. And then otherwise we would again kind of do, let's say we only return the error, we can do something like that. Write and then bytes, right? And then return error. As you can see, we didn't lock ourselves into a single implementation. We barely mentioned that anything that implements this writer interface is okay for us, right? And we will call write on it. And it's very easy then to use it. The users of our send survey function will do maybe something like, so let's say it's an example, right? Let's take file as an example. So we can open some file. Let's say OS open maybe survey.out. I want to export it there, right? Check the error, obviously. And then otherwise I could do, so we need to define the survey, right? So that would be maybe some survey with some title, my survey. And we can do called send survey as and file, right? Because file implements the io.writer. And so the substitution part of it is that we can replace this second argument of our send survey function with anything that implements obviously some sort of interface. Here in this example we used a file, but imagine it could be anything that implements this interface. For example, it could be let's say sending to a TCP socket and so forth. By the way, it's type here, it's not example, it's example, right? But it doesn't matter. Okay, let's jump to the next one. Number 4 is called interface segregation principle. And this is really used in Go pretty much everywhere. It states that clients shouldn't be forced to depend on the interfaces they do not use. This encourages creating smaller, more focused interfaces rather than large and monolithic ones. And again, Go's IO package is really a great example. So we have writer, right? We also have the write seeker, for example, that kind of embeds two interfaces in it. There is also reader, read closer, write closer, right? So we can see them here. So there are small units that could be composed if you want to, but it's not a single monolithic interface that does everything, right? But I don't want to just mention IO writer and then be done with that. So let's implement some interfaces of our own related to survey struct, right? So maybe questions, right? Because surveys obviously consist of question. So package, right, it's not main. And let's say we can have various types of questions. They all have titles, for example, let's say a label on the top, and some questions have options, like let's say it's a multi-select box and maybe checkboxes. So we could do that. We can do question as interface, and we would ask kind of implementation to have these following functions. So set title, right? So title string, then maybe also add option. Maybe there is some option there as well. Maybe let's have option also as string for simplicity, right? And the first implementation would be, let's say type, let's say it's text input question. That maybe just has a title only. So it's unexported title field, right? And because we want to implement the question interface, we would do function. Let's do text input question. So it would be, what did we want? Set title. And that would be question.title equal title, right? And we can do the same for the option, but there is a problem here because text input doesn't need any options. So what we could do, right? All right, we can just skip this function, don't do anything here. And we will use the set option in another type. Maybe that's called dropdown. So let's call it a dropdown question, right? So the dropdown question also would have a title, and also we'll have maybe the list of options to select from. Right, so we'll change it here, and here we actually need the implementation. So maybe, so we have options. Yeah, let's do simple append for now. So it's not bad, right? We already follow, by the way, some principles here. So we have the question as an interface, and it's kind of extensible. We have the implementations of text input and dropdown, and if you want to, we can have another question type. Let's say it's text area would be maybe the same, but could be kind of list of checkboxes or radio buttons. So, but this add option method on the text input question actually sticks out because we don't need it. and it actually violates the interface segregation principle. So to solve it, we can do something similar to IO writer approach. We could also create, so there is a question as kind of base question, and we can have question maybe with options, also interface, and we can use composition in Go here. So we can have a question and then move add option from here to here. Now our text input question doesn't need to implement this question with options interface, so we can get rid of this add option, and drop-down questions will remain as is because kind of it inherits set title from the base question interface as composed here. And yeah, it's a little bit better, a little bit smaller interfaces, right? And the last principle is dependency inversion principle. It states that high-level modules shouldn't depend on the low-level modules. They all should depend on some sort of abstractions, right? In simpler terms, dependency inversion principle tells that your code should depend on some sort of abstractions and interfaces rather than concrete implementations. And that kind of reduces the coupling between different parts of your software and also improves the testability. So let's jump back to our survey example and let's open the survey file where we have this repository thing. And I'll keep it as is because we maybe use some of that. And add another thing called survey manager. So let's have a type called survey manager that maybe does many things, but mostly it needs some sort of store to save surveys, maybe to pull them from. So we'll call it survey manager. So it's a struct and it has a store. And maybe I'm kind of developing this and it will be all in memory. And I put the store in memory repository, and then maybe I also have some new constructor, right? New survey manager that returns survey manager instance, and then defines store as this instance of in-memory repository, right? Which will kind of work well, but very limited and not really extensible. And the bad design here obviously is that our high-level module survey manager relies on this lower-level module in-memory repository. And what makes it even worse, let's say it's not maybe in memory, it's even something that's harder to spin up, like Postgres database repository. And then we want to cover this piece of functionality with unit tests. It will be really hard and we'll need to restructure our code because out of the box it won't be possible. So again, interfaces and constructors can help us here. Instead, we can tell our new server manager constructor to receive the store, which also again does need to be a specific implementation. Since we already have the repository interface, we can do that here. And yeah, we can simply pass it right here. Obviously, we'll need to change it here to repository. And it works because we already did some pre-work. So we already have this repository interface defined here with the save method, and it's really swappable now. For example, in our unit tests, we can pass actually here some sort of mock repository, or in-memory repository, but would also work in unit tests. For production use, we can read it from configuration and maybe construct the Postgres repository if you want to do so, or also switch to something else, right, without changing the code. The specific implementation details may vary depending on the programming language. For example, in Go we used interfaces and composition, while in other languages you could use inheritance, for example, but the core tenets of Solid remain applicable everywhere. And I truly believe that embracing those principles can lead to more robust and testable code. So yeah, let me know in the comments below. Do you like those principles? What other software design principles you like to follow? Do they actually really matter in the world of LLMs? And yeah, don't forget to subscribe and see you.